All right, the product of a non-zero real number a and its multiplicative inverse, or called reciprocal, a to the negative 1, is 1 over a. If you multiply a and its reciprocal, you get 1. That's normal. We've known that since, like, hopefully pre-algebra, middle school. 1 is the multiplicative identity. Similarly, many square matrices, A, have a unique multiplicative inverse matrix, and you see it is denoted just like the integer was denoted, A to the negative 1. Defined so that the product of A and its inverse is the identity matrix, all right? Remember, for us, identity matrix, all of your diagonals are 1, or the first diagonal is 1 and everything else is zeros. That's your identity matrix, okay? And so all it's saying is, just like in integers, if you multiply an integer and its inverse, you get the identity, which is 1. If you multiply a matrix and its inverse, you get the identity matrix, which is the one diagonal. All right, and so that's one way that you can prove, do you have inverses? You can just multiply them. In this case, so normally multiplication of matrices is not something that you can change the order for, right? It's not commutative. But for inverses, it doesn't matter which order you multiply them in, you should still get the identity. So if you just multiply A times B and you get the identity matrix, then you know that you have inverses. And so the first thing we're going to do is just prove, do we have an inverse? So we're going to take 2, negative 1, 5, negative 3, and multiply it by 3, negative 1, 5, negative 2. Since they're square, we automatically know if they're both 2 by 2s, they're going to multiply, and you should get a 2 by 2. And so you do the multiplication out. All right, which hopefully we all know how to do at this point. And then negative 1, negative 1. Nope, I did this. There we go. 5, negative 1. All right. And so you'll see that you get 6 and negative 5, that is a 1. Negative 2 and positive 2, that is a 0. 8 and negative 8, that is a 0. Negative 5 and positive 6, that is a 1. So that's what we're looking for. Yes, those are inverses of each other. All right, easy enough. What we're going to focus on this section is finding those inverses, okay? So there are ways to find inverses for a 2 by 2 and then for a 3 by 3, and we're going to talk through that process a little bit. For a 2 by 2, to find the inverse, it is defined this way. We find the determinant. Remember, the determinant looks like the capital letter with absolute value. That's what the determinant notation looks like. So we find the determinant and we use the reciprocal of that. All right, we do not negate it. Whatever it is, we use the reciprocal of it. So we just flip it. And then we multiply that by the original matrix moved around a little bit. For the first diagonal, we switch those. So you see that A and D switch places. For the second diagonal, we negate those. It doesn't mean they're negative. It means they're opposite of whatever they were. Okay? And then once we do that, we multiply it through. If we are stopping there, so we're stopping at the inverse, you want to reduce your fractions, okay? If you are moving on to use the inverse to multiply, you don't want to reduce your fractions because you automatically have a common denominator, okay? Unless they all reduce to whole numbers. But if you have fractions left over, you want to reduce it if you are just stopping at the answer is the inverse. You want to keep them if you are moving on to multiply. And we're going to move on and multiply later on in this section. So let's look at just finding the inverses. Find the inverse. So when you're finding the inverse, the first thing you have to do is you have to find the determinant. So we're going to first find the determinant of this guy. The determinant is going to be 8 minus 5. So my determinant here is 3. All right. Now we're going to take that determinant. We're going to do the reciprocal. The reciprocal of 3 is 1/3. And we are going to multiply, scalar multiplication. So we're going to like distribute through. We're going to switch this 4 and 2. So we're going to make that 2 and 4. We're going to negate this 5 and 1. We're going to make that -1 and -5. And then we are just going to multiply that through. So we'll get 2 times 1/3, -1 times 1/3, -5 times 1/3, and 4 times 1/3. That is my inverse. Can I check it? Yes. How could I check it if I wanted to? So if you, by chance, want to check it, you can multiply it through and say, is this the inverse? I should get the identity matrix if it is. Let's look at this next one. There are situations where an inverse does not exist. First thing I'm going to do is I'm going to find my determinant. My determinant here is negative 12 plus 12. My determinant here is 0. I cannot find an inverse for this guy because the first step is then to do the reciprocal. 0 does not have a reciprocal, right? I cannot multiply anything by 1 over 0. This does not work. So in this case, I would say this has no inverse. So no inverse for this guy would be your answer. You would stop there. There is no inverse. We have this little shortcut for a 2 by 2, right? But really the process by which they originally came up with this is using augmented matrices. So basically what I mean by that is we have this 4, 1, 5, 2, that's our matrix here. And then we have the identity matrix over here, okay? And this 4, 1, 5, 2 is the one we did from example 2, right? This is the 2 by 2 that we just did. So we have the original on this side, the identity on this side. If you make the original look like the identity, then the right side will be your inverse, right? So if you use your row operations here, in this case, they... negative 5 times r plus 4, negative 5 times 1 plus 4 times 2, they zeroed out this guy, right? And then they divided everything by 4 to get this row. And then they multiplied this through to get rid of him. I don't know why they have one. Oh, here, 1 negative 1/4. Multiplied through once they divided the 3 out to get this 0, and then we got this. So they just did row operations. They changed the left side, my original matrix, into my identity. And when they did that, they really had inversed everything is what they had done, which created the matrix inverse. And if you look at our answer from example 2, this is your inverse. 2/3, negative 1/3, negative 5/3, and 4/3. That is our inverse. And so that's the process by which it goes. But using the determinant and flipping your diagonals is the shortcut versus going through the row operations to get it, okay? And so when you do a 3 by 3, that's the process, okay? The process is to take your original matrix, which is this guy right here. To the right of it, put your identity matrix for a 3 by 3, which is a diagonal of 1, all zeros, right? And then convert that left side into the identity matrix. And by the time you get done with it, the right side will be your inverse, okay? Now I will say, I don't know if you think this process looks tedious, but that's a pretty tedious process there, right? It's different when you're solving maybe a 3 by 3 and you just have one column over there, but now we have 3 full columns over there. And so this makes the process more tedious. And so this is a place where you can use technology. So we're going to look and see how to use technology to do it. Same process as before. You would have to go into your matrix menu. You would have to enter your 3 by 3 matrix as a matrix in your matrix menu, okay? And then from your main screen, you would pull in that matrix. So from your main screen on your calculator, you would go into your matrix and you would choose the matrix you have loaded. In this case, their matrix is labeled A. And then on your calculator, you have an X to the -1 button. So you click your X to the -1 button and you see that you have this now matrix to the -1. Now, if you just do that, you're going to get decimals. Unless it's all whole numbers, you're going to get these crazy, crazy decimals, which we don't use the decimals typically for matrices. Typically, we keep them in fraction form. So then you can go into your math menu on your TI. And from your math menu, usually the very first option is this arrow fraction, which means calculate this, leave it in fraction form. And so if you choose that option and then hit enter, you will see that you have that same inverse that was created by doing row operations. So if you set this up in a manner that it looks like an equation, it makes sense, right? So for example, I'm going to set this up with my coefficients. And I'm going to say I have 3, -2, 4, and 3. That's my coefficients. And you can think about that like, well, those are my coefficients, and they are all being multiplied by x's and y's, right? So if I did row operations, I would say I'm going to end up multiplying the 3 by the x, right? And the 2 by the y, because that's what that is, right? That's 3x and -2y, 4x, 3y, right? So if I did matrix multiplication, you can see that that's how they line up, and that's why one goes down. And those equal then a matrix that looks like this, okay? So if this were just a standard algebra problem, and I had something like 2x, all right, equals 5, I would multiply both sides by the reciprocal, right? I would multiply both sides by 1/2, or by the multiplicative inverse, so to speak. And so that's exactly what we're doing here. We are going to take the multiplicative inverse, and we are going to multiply it over to this side, and that will leave us with our answer for our variables, okay? And so that's what we're going to do. So we're going to find the inverse. First step here is find the inverse. So how do I find the inverse? Well, I have to find the determinant. So I'm going to, if it will let me, technology here. All right, so I'm going to find the inverse. So the first thing I need to do is find that guy. So 3 times 3, that's going to give me 9, minus a -8, or plus 8. So my determinant here is 17. I'm going to take 1 over 17 and multiply it through. Now, 1 over 17 likely is not going to reduce, right? 17 is a pretty large prime. But if they would reduce, this is where I would tell you not to reduce them. The 3 and the 3 switch places, but they're the same number. The diagonals negate, so that means my 2 becomes positive, my 4 becomes negative, and then I multiply that through. So I get 3 over 17, 2 over 17, -4 over 17, and 3 over 17. This is the point, because I'm about to use this inverse to do multiplication, and multiplication of matrices adds the products, this is where I would not reduce, even if it could. So for example, if that was a 9 instead of a 17, I would not reduce those 3's to 1/3, okay? Because then I would have to go back and get a common denominator when I multiplied and added, right? And so this is naturally going to give me a common denominator, so keep it. Don't reduce it. The only time you reduce these, if I say find the inverse, then your final answer needs to be in simplest forms, the inverse, okay? But at this point, I'm not going to reduce even if I could. What would I do over here? Well, I would say 1/2, multiply both sides, 1/2 times 5. Now, normally with integers, order doesn't matter, right? So I could say 5 times 1/2 or 1/2 times 5. Here, order matters because I am doing matrix multiplication. So when you are doing this process, you always want to list your inverse first, okay? So you want to say inverse times this answer matrix and multiply in that order, okay? If you tried the other day, way it wouldn't work, by the way, right? A 2 by 1 and a 2 by 2 can't multiply. But just make sure that you keep that in mind, that you are doing inverse first and then answer. And then you're just going to do matrix multiplication. So we're going to do row by column here, right? So we're going to say 3 times 12, 2 times -1, right? And that's my first. And then we're going to say -4 times 12, and then 3 times -1. All right. So we have 36 minus 2, we get 34 over 17. -48 minus 3, that's -51 over 17. This is going to equal my x value. This is going to equal my y value. So I'm going to get 2, -3, which means my answer is going to be 2x, -3y. That is my answer. And just like any systems of equations, you can check it by plugging them in. You just found your x and y. Plugging them in should give you a true statement. Mr. Jones wants to invest $100,000 inheritance into aggressive growth mutual fund with a projected return of 10% APR, a municipal bond fund with projected return of 3%, and CDs with a 2% APR. How much do you invest in each fund if he hopes to earn $6,300 and wants to invest as much in the mutual funds as he does in mutual bonds and CDs combined? All right. So, first thing, we have 3 different funds. So we're going to call those funds X, Y, and Z funds, right? Which means this is how much he's investing. X is how much he is investing in that fund, Y, X, Y, and Z. That's how much he's investing. So if I add up how much he is investing, how much is that all together? Well, that's $100,000 according to my word problem. Then I look at how much he's earning on each one. Well, on X fund, he's earning 10%, right? We can ignore the zeros. We're going to ignore those and probably add some. Yeah. So I'm just going to say 10x, not 0.10. I'm going to bump my decimals over just because I don't want to deal with decimals. 3%, right? So that's just going to be 3y. And then 2%, that's going to be 2z. And if he wants 6,300 and I have bumped all my decimals 2 places, I need to do 6,300 and bump that decimal 2 places as well, by the way. Just so you know. If you choose to do that method, do it all the way across, okay? And then it says he wants to invest as much in the mutual funds as he does in the bonds and CDs. This one's not as intuitive, but if he has the same amount in X as he does in Y and Z, then if he subtracts X minus Y and Z, he should get 0, right? Does that make sense? So if I have my X and I subtract my Y and my Z, I should get 0. If it's the same, if X is the same as Y and Z combined, does everybody agree with that? 10 minus 7 minus 3 is 0, right? Okay. So what do I have here? I have a 3 by 3, right? I can solve this with inverses. So this is where I'm going to do this in my calculator. In my calculator, the first thing I'm going to do is I'm going to set up 2 matrices. 2. I'm going to set up a matrix for my coefficients, which looks like this. Okay? So I'm going to set up some matrix in my calculator to look like that. I'm going to set up a second matrix. This guy's going to look like this. Okay? And then I'm going to use my matrix functions. I'm going to pull down my A and do the inverse, right? And then I am going to multiply that by what happens when I pull down my B. Okay? And I'm going to find the product. Now, because this is in money, it's okay if it returns decimals. I don't think it does. I think it returns something like this. 50,000, because we're running out of time here. So we'll just put these. What does this tell me? Well, this tells me my X, my Y, and my Z. This is telling me for him to invest 50,000 in my X fund, 30,000 in my Y fund, and 20,000 in my Z fund, right? And so this is where knowing the concept of a 2 by 2 is going to help you when you have a huge 3 by 3, because you're going to know, okay, I need my inverse of my coefficient matrices, and I need to multiply that by my answers. All right? All right, so this is legit. I mean, this is something that people would use, especially if you think back, if you're a history person, you think back like World War I, World War II era, when they would encrypt messages to make sure that the enemy did not understand what they were trying to say. They used a generic one here. So they just did A, B, C, D, E, F, G, all the way to Z, 1 through 25. But no, they did 0 through 26. Okay, I was like, that's not enough letters. So A was 0, that's why we ended on 25. All right. And so then they did, God is my joy. Okay, that's just a generic phrase here. And they used 2 X's at the end so that it would be a square matrix when they did this. So they just labeled these by the letters that they are. And then you can see they just pulled these down. They added these so that they would have a square. That's why they did that. Then they have an encryption matrix. All right, so in order for Carter to know my message, he would have to know my encryption matrix, right? So what I'm going to do is I'm going to multiply by message weight by my encryption matrix, and I'm going to get the code, and I'm going to send it to Carter. And then he is going to multiply that code by the inverse of the encryption matrix to get the actual code and decipher it. All right, so this is what they would actually do. I mean, this is how they would create ciphering, right? Which is kind of cool to me. I like this process. I think it's really cool.